All right. Okay. So, welcome to today's class. Let me start off by going back to this page here. I have updated the syllabus schedule. I realized the one I had was old because I wanted to have MPI and OpenMP on the days I was away. That's what my postdoc Lucas is going to present to you. MPI and OpenMP are two of the more practical tools that are used in high-performance computing. So, Java is used by IBM and companies in a lot of contexts, but if you want to do like simulations of science stuff, generally speaking, you're using C, C++, MPI, and OpenMP for your parallelism. And he's going to talk to you about those tools and some of their unique challenges when he is visiting as professor. All right, so we're not going to go over the homework because I'm going to extend it. Cool? So those of you who haven't figured everything out yet, you have a little more time to figure it out. I'll extend it by a couple of days, maybe to Monday or something. Yes.
You can go over the quiz question.
I can go over the quiz questions. All right. That'll be fine. Okay. Okay. So student IDs. It turns out your student IDs are no longer in Moodle. And so I just have to believe whatever you put. So long as you all have different things, everything will be fine. But whatever. All right, so the first question was what speedup will be achieved for a code that is 75% parallel when run on 3 processors? So that's checking to make sure that you remembered Amdahl's law. You remember Amdahl's law? So basically, though, what is going to happen here is the parallel section of the code is 75%. So the non-parallel, the serial portion, is 25%. Now I'm going to take that 75% and I'm going to run it on 3 cores. And that's going to divide it by 3. So that's going to be another 25%. So 25 plus 25 is 50. And 50 is a speedup of 2. So if I wanted to actually use the Amdahl's law formula, which might be more comfortable to your brains, what I can do is I can say Python, I could say def a x say pn, right? And I can say return. Now the Amdahl's law is 1 over 1 minus p, that's the sequential part, plus p over n, right? That's the formula. So a 0.5 and 2, or 3. Speedup of 2. Right, just plugging it into that formula gives me 2. Any questions? All right, I expect you to know Amdahl's law. Yeah, well, you need to be able to. So the formula, the derivation of the formula, I think is simple enough that you can internalize it. And if you internalize how you get it, right, then it's easier to remember. So the logic was you take the speed up is the old speed divided by the new speed, right? So if it runs at half the time, if it runs in half the time, that's a speed up of 2. If it runs in a tenth the time, that's a speed up of 10. So that's kind of a logical way to do it. So the old time divided by the new time. And then we look at the time it takes to run the application. We have the serial portion and we have the parallel portion. And what we do is the serial portion is just going to be the serial portion. It's going to take however long it takes. But the parallel portion, we can divide by n. And knowing those few simple things, that gives you that formula. Okay. All right. And then there were the true-false questions. The use of mutexes creates a danger of deadlock. True. Preventing four-way red is a safety property for traffic intersection. Well, four-way red is safe, right? It's just kind of going to slow you down. In fact, you probably want it for at least a moment. So that's not true. A lost wake up is caused by a failure to unlock. This is testing whether you remembered what a lost wake up was. This is false, right? So a lost wake up was when we did, remember we had await and signal. And we had two processes waiting on that signal. And we were only signaling when we transitioned that queue from 0 to 1. And as a result, one of those things got woken up. Well, the way the events played out, I can reproduce it if you want details, but the way it played out is one of those processes that was waiting for that condition didn't wake up to check and see that it was able to run. So that was a lost wake up. And we fixed it. Do you remember how we fixed it? Signal all. Good. Okay, so if you knew what a lost wake up, you got that one okay. A monitor watches parallel access of data. So this is this question was testing to see if you remembered what a monitor was. A monitor is an object that has its own locks and condition variables, and it uses them internally. It has nothing to do with watching anything. So this is false. Yes, Tristan.
So a monitor, like, is just the locks and the condition.
The locks and the conditions are built into the class that needs them. So one of the problems, right, if we have a queue with an NQ and a DQ on it, and we want to access that queue by multiple threads, if we just have a mutex, we have to remember that every time we access that queue, we have to put that same mutex. And that makes our code brittle and difficult to manage, right, if we want to change things. And it gives us the possibility of forgetting to use it, right? But by taking that parallel logic and encapsulating it in the class to make a monitor, right, you have more robust and safer code.
Yeah, so I guess what I'm wondering is like how, like, the monitor definition doesn't necessarily mean that it has to watch over data. It's just
Right. The monitor just means a class that contains its own locks and condition variables.
It doesn't necessarily mean it watches over.
Doesn't watch over anything. That's nothing to do with what it is. Yeah. I was just playing off the words on that one. So.
Could you maybe argue that one could be true because most of the time when you have a monitor, it is watching over some kind of parallel access of data. Right?
I mean, the point of the question was to see if you understood that the definition of a monitor is a class that has its own locks and condition variables, and that's different than that. So, today is what's today's date? The 5th, 4th. All right. A condition variable should never be used with a while loop. Well, no, it usually is used with a while loop. Preventing four-way green is a safety property. Yes. A mutex can be used to safely access shared data. Yes. I mean, it can be safe. It isn't guaranteed, but it can be. Okay, so that's the quiz. Any questions? All right. So the basic rule for this course, well, I'm going to, if all goes well, I drop, 2 to 3 quizzes at the end, and I like to give lots of quizzes to give you lots of chances to find your way, right? But the things I expect is when I give a definition, I expect that to be ready for that. When I give you a piece of code, like today we're going to talk about the Peterson lock. When I give you a Peterson lock, I expect you to know how a Peterson lock works. And if I show you a code that's similar but different, I expect you to be able to understand either what's wrong with it or what's right with it or whatever. Yes.
First quiz was curved. Is everything going to be curved?
Everything is curved. So the logic behind my curves, it's automatic. So I want the curve to be 75%. And so what I do is if you're below, I figure out the average, and then I move everyone below that average, I scale them up by a little bit, and then everyone above that average gets scaled by less, right? So it's not a curve so much as it is 2 lines, right? And so if you got 0 points on something, the curve doesn't help you. I used to give people credit just for taking quizzes, but then I found that people were able to game the system and pass the course without understanding things, and I felt stupid. I got outsmarted. But anyway, so that's how that works. All right. Let us go back to the slides. I think these are in the right place, if I remember. No, that is not the right thing at all. That's totally wrong.
We're at the end of the bakery algorithm.
We were at the end of the bakery algorithm. Very good. I thought we were at a different place. We were in chapter 2. We were at the yeah, I think you're right. The end of the bakery algorithm. Wait a minute. I didn't do the filter lock, did I? I think I was at Peterson's lock. Yeah, I'm just gonna start with Peterson's lock. Maybe I did it. I'll just cover it again. It won't hurt you too much, I hope. Yes, I think I did Peterson's lock. So Peterson's lock is the same as we said as the lock number 3 from the first chapter. The victim is the can, and the 2 flags are, well, the flags. And the logic is that I signify that I'm interested in getting the lock by raising my flag, by setting that to true. And I then proclaim myself the victim. And this gives me a lock. And when I'm done with the lock, I just set my flag to false. So I have 2 types of variables. There's a variable that only I write to, and that's a flag. And then there's a variable that both threads write to, which is the victim. But thread 0 only writes a 0 there, and thread 1 only writes a 1 there. Right? So those are the different ways that we can use variables to coordinate in memory. Now, if you take this code exactly as it's written and you implement it in Java, and then you test it, and you say do that same thing I did with a counter, and like in that first example, and you run it for say 10 increments of that counter, it's going to work perfectly. But somewhere around 1,000 or 10,000, it's going to start failing. And the reason it fails is because of the way Java handles memory and stuff internally. So everything that you're doing, ideally, should be an atomic variable in order for Java to synchronize it properly. So this victim could be an atomic int, and the flag could be an atomic array. And alternatively, the victim could either be an atomic integer, or you could put a volatile tag on there. The volatile tag says that I always have to keep the memory current. It doesn't apply to an array like it does to an individual variable. So you can't use that on the array, but you could use atomic in both places. All right. Any questions? Ryan.
Why doesn't the compiler just make everything atomic?
Because that would get lower performance. Right? So instead of giving you robust safety, we try to give you performance.
Mm-hmm.
And it would be nice if there was like a compiler flag that you could tell, make me safe. Don't hurt my head like this. But that's just not in the cards. Okay, so flag I equal true, announce you're interested, defer to the other, and then you wait. And the other thing I told you that I like to do is inside that curly bracket, whenever I do a wait loop, I put a thread yield, right? To not waste time to the extent that I can manage. And there's your unlock method. Okay, so it's deadlock free, it's starvation free. Those are things we said before. Make sense? Right? It's starvation free because the next time I try to get that lock, I have to make myself the victim, and that will let the other one through. Now, the filter algorithm, the filter lock, is essentially the same thing as the Peterson lock. It's just that I do it n times. So if I have 3 threads and I want a mutex, a Peterson lock won't work. A Peterson lock will only work if I have exactly 2 threads, right? I need thread 0 and thread 1 and nothing else. The filter algorithm has what they call waiting rooms. So you imagine that I still have flags and I still have a victim variable, but now I'm going to share it with n different threads. Okay. So two changes I'm going to make is, well, first of all, the victim thread, we're each going to write our own thread ID there. That's going to be the same. That's going to work exactly the same. It's just, and now instead of 0, 1, it's going to be 0, 1, 2, 3, 4, 5, whatever. Okay. As for the flag though, the flag is going to raise multiple times. So if I have 2 threads, the flag has up or down. If I have 3 threads, the flag goes up once or twice. If I have 4 threads, it could go 1, 2, 3. So the way this is going to work is I'm going to have rounds at each level. We're going to do the same thing that we did with the basic Peterson lock. We're going to raise our flag to that level. And then what we're going to do is we're going to declare ourselves the victim. And then we're going to go into that same loop and we're going to look and we're going to see if we are the victim and there's somebody else with a flag raised to that same level, then we're going to spin. That will stop at most 1 thread, right? So I had 10 threads and we all try to write victim in there. Only one of us is going to wind up being the victim, right? So if I have 10 threads and I go into that first level, I'm going to come out of that with 9. So on that next level, I'm going to write my victim into that and raise my flag to the next level. And I'm going to say, how many people have flags at my level? And is there more than 1? And am I the victim? And so each level, I can reduce the number of threads by 1. All right. And that's how it looks. So each one is going to go through. And this is how the code looks. We're going to have the thread ID.get. We're going to have the level and the victim. It's going to be n for the number of threads. We're going to initialize the levels to 0. So that's the levels of the flags. They're going to start at 0. And then when I lock, what I'm going to do is I'm going to go through the levels starting at 1. I'm going to set the level to the level I want. I'm going to set myself to the victim on that level. And then this isn't real code, right? Because there exists in Java. But so while there exists another thread that is at my level or higher, and while I am the victim on my level, I'm going to spin. And right. And when I complete that loop, when I can complete all those loops, I'm going to be done. I'm going to have the lock. And let me just I have this coded, but I don't have my IntelliJ open. Trying to make myself use IDEs. So when I learned how to program in the 80s, all we had was ED, which I ran on which is an editor that runs on a printing terminal. And then I graduated to VI and I just kind of got stuck there. Any of you even know what VI is?
Yeah.
It's a very primitive, it's infinitely complicated, I guess, but it's a very basic editor with no fancy stuff in it that you're used to from IDEs, no AI or anything like that. And it doesn't do code completion for you or anything. It just gives you a basic window into a file. Yes, it is a text editor you have to access through a command line. And I know all the keystrokes for it that I don't even have to think them. They just come out of my fingers. So
Plug in and use the demo and stuff.
You know, I feel like when I go into IntelliJ, I don't want to do the Vim commands. I want to do the IntelliJ commands. I don't know why that should be, but you'd think I wouldn't. But anyway, um, so here's my filter lock. And I have to use the atomic integer arrays. And I create two of them. I set them to 0. So setting looks like set I comma 0. And then lock, I go through the levels. I set the victim, I set the level. And then I have this for every method, which I coded to look like this. So for k equals 0, k less than this dot n, n is the number of threads, k plus plus. If k equals me, continue. If level get k is greater than or equal to L, and victim of get L is me, then return true, else return false. So, wait a minute. Okay. And so this is where I came from, right? And so while that thing is true, I'm going to spin. Okay, I'm going to say thread.current thread.yield. And that's how you do the lock.
Find the for every method.
Yeah, so the idea is what I'm going to do is I'm going to iterate through 0 to n, which is the number of threads. And if I'm on my if the thread is equal to my thread, the me thread, where is me oh, it's passed in, right. If k is equal to me, then I'm going to skip that one. So I hit continue. And then I'm going to check to see it at my level, is that k, does that flag raised to my level or higher? And if so, am I the victim? And if both of those things happen, I return true. Yes, Reagan. I can. So anyway,
So the flag on that.
right. That's what this first thing, it says, does thread K have their flag up to my level or higher? That's what that highlighted part right there is doing. Right? It's saying it does is that. And then I'm going to use this loop to go over all the threads. Right? I have a little max threads method. And then I have my testing system. So whenever I write code, I build something to test it. Because in my experience, no matter what I've learned is no matter how smart I think I am, and no matter how much experience I have coding, if I don't test something, it does not work. It's just an invariable law of nature. And so what I'm going to do, right, I'm going to have this, I instantiate this filter, I pass it to my test method. Let's go to my test method. What my test method is going to do, it's going to use my lock impulse. So my lock, that is an interface that has 3 methods on it. It's got lock, unlock, and max threads. I thought, I thought it was Control Alt back arrow. Okay, it is. All right. And so what I'm going to do inside this method is first I'm going to get the number of threads that I'm supposed to have, and then I'm going to create a set of I'm going to single counter, single static counter, and a bunch of local counters, and I'm going to initialize those. And then I'm going to populate this list. I'm going to create threads. So thread.add, and this is going to be a new thread, which they've somehow elided to. Yeah, okay. This is going to be a new thread. It's got a public void run method. And inside there, I get the current thread. I call lock. I increment the counter. I increment my counter, and then I call the unlock, right? And then I start all the threads and I join all the threads. And then I print out all the local counters and I print out the global counter. And then I have an assertion statement to make sure that my number is what I think it is. And if any of those things are unfamiliar to you, raise your hand. All right. And I've got my assertions enabled. Shoot. Okay. All right. So now let's go to my filter class and run it. And there you go. So it ran with 6 threads. It ran 100 each, and it worked. I can go in there and I can make this 1,000, and I can run it. And it works. And you notice what happens is each thread seems to do an equal amount of increments. And that's because, right, that it's very highly contended, and these levels have the same fairness property as the Peterson lock. So they tend to follow in line. They tend to be almost waiting in line to get through. So we almost get perfect fairness. We're going to talk about the bakery lock next, which guarantees it, but you almost get it with the filter lock. Any questions? Yes, Tristan.
Why would you use the third lock over another? Ties one being just like a better.
So in real life, when you're programming, you're going to use lock. You're going to use reentrant lock probably for everything, and you won't think about it again. But the reason we go through these exercises, right, is because first of all, it shows you how parallel logic works, right, on some very simple things, so that you can get your brains used to the complexity of it. And after we go through, none of these locks that we're working on now are things that anybody uses, right? We have something better, and we're going to teach you. But this is how computing started. So we started with these locks, and then we realized there was a better way, and that we needed a better way. Because look at this stupid filter lock, right? I'm sorry to call it stupid, but I want to have, if I have 100 threads, then I have to have 2 arrays of 100 just to implement the lock? Really? Yeah, I need to use all of this memory, and then if I have a bunch of locks, each of them is that big. It's crazy. So there is a better way, and we are going to get to it. But the point is to understand the logic. It's kind of like I'm teaching you to be a mechanic, right? If you want to think about it that way, I'm trying to teach you to be a mechanic, and a mechanic has to take their car apart and put it back together. And maybe, after you leave that, you don't take apart your car anymore. You don't take apart certain things anymore. But you need to know how it works in order to do your job. And so that's why we're doing this. But choosing one lock over another, at least for most applications, isn't a thing that you would do. There are circumstances where it might be performance critical, and then you might put some thought into it. And then we're going to have some special locks that we're going to show you for that, including a lock I invented. So, all right. What's that?
It's a lock that you.
Oh, you'll see it later. You're not ready for that yet. I want to show you other things first. Okay, let's go back to the slides. All right, so right. So we start at level 1. At most, n minus L threads enter each level, and mutual exclusion arrives at level L equal n. There's no starvation. Filter lock satisfies the properties of the Peterson lock at every level, so no one starves. But are they completely fair? Threads can be overtaken, so it's not completely fair necessarily, although our experiments tend to, with our high contention showed that, at least in that circumstance, it was. But maybe we want stronger fairness guarantees. We want a thread not to be overtaken too much. So if A starts before B, then A enters before B, right? But what does start mean? And so we need to make some adjustments to this. We're going to divide our lock into 2 parts. We're going to have a doorway interval and a waiting interval. And the doorway is going to always finish in a finite number of steps. And the waiting interval is going to be unbounded, but we're going to wait in order. So for threads A and B, if the doorway of one thread completes before the other's doorway, then the critical section of if door A is if thread A enters the doorway first, then thread A's critical section will run first. And B cannot overtake A after they get in the door. Make sense? The filter lock satisfies the properties that no one starves, but there's a very weak fairness. And bakery algorithm is going to give you first come, first serve. And the question is, how does it work? Well, you're going to take a number and you're going to wait until the lower numbers have been served. So that gives you and to implement this, we're going to use what's called the lexicographic order. So I have a tuple that is two integers, right? A and I, and B and I, and we want to compare them. So we say if A is greater than B, then this is true. But if A is equal to B, then we go to the second thing and we check I and J, whether I and J are equal. All right, make sense? Good. Okay, so the bakery algorithm looks like this. And you know, this is this is maybe something I should change on these slides. It says label here, but you could just put int. Int would be fine here. I don't know why they chose to use label. It isn't a real type, but anyway. So you could just have an array of flags and array of labels. And then in your lock method, what you're going to do is you're going to raise your flag to true, and then you're going to get your label by looking at the maximum of all the other labels and adding 1 to it. So you're going to pick something that's larger than anybody else's. Now, of course, there's a danger, right? If two threads do this step at the same time, they might get the same number, right? So that's why we have the tuple. So what we're going to do is we're going to use a combination of the label and the thread ID to determine an ordering, and that will give us a total ordering of the threads. And so while there exists another thread that has a flag raised, and it's not us, and their label is superior to us, we're going to wait. So that's the basic idea. So just getting our ticket and then waiting for our ticket to come up. Make sense? And of course, I always forget that on my slides that it does this little walkthrough thing. And I describe the complete thing without doing the walkthrough, but there it is. Okay. And then the unlock is we're gonna lower our flag. And the labels are always increasing necessarily, of course. And there's always one thread with the earliest label, and ties are impossible, of course. And the reason is
They have the same number.
by the thread ID. Yeah. Good. And so this does all the things we want. If we go through the doorway and A is before B, then A's label is smaller. And so we have a right for label A, and then a read of label A, and so on. And B, if B sees a smaller label, so B sees a smaller label, and well, okay, I'm not quite sure how to talk about these words here, but I think we've explained it, right? We say the flag is true to signify our interest. We get the label, and we look to see if we are the earliest label. And if we are, we exit the loop. Okay, mutual exclusion. So suppose A and B enter the critical section together. Suppose A has an earlier label, then B would have seen it, and therefore flag A is false or label is the other way. So either is impossible. So this is sort of our proof by contradiction logic that the slides like to do. And that shows us that that helps us reason out that this will work. Any questions? All right, and that's it for chapter 2. And we still have time, so I can go on to chapter 3. Unless you have more questions. Yes.
You said you were extending the homework. When are you extending it to?
I think Monday. And another thing I could show you, I've got a bakery lock. And here's my bakery lock. Right, I just use wherever they have the labels, I just use int, and I get a I have a max label method, which just goes through all the labels and computes a max, if the label is higher, then it finds the maximum. And I just set the max label here. And this was how I did the logic. I think I did it better in the filter lock. I have this, so I have this while true, and I have an outer tag on it. And then I go through each of the Ks. And then if the K is equal to I continue. And if my flag is raised, and if there's a label that's lexigraphically smaller than mine, then I sleep for 1 millisecond. It's interesting. I wonder why I chose to sleep rather than yield. It's kind of similar. But now that I'm looking at it, I'm kind of surprised I did that, because yield is what I usually do.
Jake's it usually suggests sleep over you.
It may be that that's what happened, and I just went with what the clanker said. The AI is so dangerous, right? You have to really understand what it's doing, or its help is going to be not help. All right. Okay. So this is my unlock method, and I've got a test for it, just like the other one. And I've still run the filter lock because it's running just my last. Hold on. Bakery. What is happening here? There we go. It was just slow. Da, 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 da. All right, so it's doing the same thing. It's behaving the same way as the filter lock, really. It seems to be slower. Yeah, I think so. I don't know. Right. So by the way, if I succeed in getting through this, then I can continue to outer. Well, I mean, if I don't succeed in this, rather, I continue to outer, so it will retry this K loop from the beginning. As soon as I fail inside one of these Ks, I go back and I have to get through all of them. And if I get through all of them, then I break out of the outer loop. So does anybody see a problem with my code? Apart from being slow. There is a problem with it. I just didn't get around to fixing it. No one sees it? Reagan? Let's look at the filter lock again. There's the filter lock. Atomic integer array. It's not using atomic arrays. That means this lock can fail and two threads can get into the critical section. It can probably happen. We didn't happen to see it here, right? And so this is a good example of why parallel bugs are so insidious, right? You saw me run that. It's incrementing to 6,000 multiple times. It's working perfectly. But maybe one time in a million, it's going to fail. And you've written some, mission critical application. Maybe it's keeping a plane in the air. Hopefully not. And every once in a while, it fails, and you don't know why. And you can't even figure it out. There isn't any hope because you can't reproduce the error. And in this case, it's all based on the subtleties of the way Java shuffles memory from the main memory to the threads. And that's like the most hopeless thing for you to figure out ever, right? And as a result of this, right, whenever I write parallel applications and things aren't working, I find myself, I can make this atomic. I can put volatile on that. I can make another thing atomic. It's one of the, how you flail around for any sort of random answer when you're debugging your code. That's when I'm parallel programming, that's one of my go-to flails. All right. That was fun, right? Let's look at chapter 3. Okay, so concurrent computation looks like this. I think we've even seen this exact slide before. We've got different CPUs working on different objects. And so what is a concurrent object and how do we describe it or implement it or tell if we're right? Whoops. So we have a FIFO queue. We're going to have an NQ method and we're going to have a DQ method. And we're going to have our lock-based queue. And we have a head and a tail. Let's see. We have a head and a tail and items that we're going to lock. And logically, right, this queue is a circle. Because the head and tail can just can just increase infinitely. And we're going to use the modulus operator to keep it in bounds. So we've got a head, a tail, a number of items, and we have a lock. And then we have our constructor where we initialize those things. And now we have our DQ method, right, where we get our lock. And remember our rules about safety, right? When we get a lock, we use try finally to do the unlock. And we're going to say if the tail is the head, then we're going to throw new empty exceptions. So how you behave when you're trying to DQ something from an empty queue or NQ something to a full queue, you have to decide whether you want to have a condition variable and a wait or whether you just want to return an error condition. In this case, we're returning an error, right? We're throwing an empty exception. And then if it's not empty, we can now extract the item from the queue. So we say head %items.length and then head plus plus. And then we return the result. And then we release the lock no matter what. And that's the DQ method. And it should be correct because the modifications are mutually exclusive, right? We did it with a lock. Now consider the following implementation. It's the same thing, except without the mutual exclusion. And we're going to say that we have exactly one thread that's doing enqueuing and one thread that's doing dequeuing. And we'll say this is our wait-free queue. And I guess we have not defined wait-free, have we? We're going to eventually. But in any event, what wait-free means is each method must complete in a finite number of steps, right? So that pretty much rules out any kind of while loop. You could have a for I equal 1 to 10, right? But you can't have a while loop inside a wait-free method. That is just not how it works. And the cool thing is, even though there's no locks in here, this works perfectly, provided we have one enqueuer and one dequeuer, right? And the reason this kind of works, it's kind of surprising, but the tail is only modified by this thread, and the head is only modified by this thread. So those increments can never happen in contention like they could with the counter examples we had, right? So this actually works. And this is something occasionally comes up in my real life work, is I have a two-thread queue where I have exactly one producer and one consumer. And I know that that's a special situation for which I don't need locks. And it's a good optimization to get rid of them because they are overhead. So this is cool, don't you think? And it's just sort of a magic one-off thing. It's one of these things that you just keep in your memory. It's like So you know how you're in calculus. One of my favorite things is how do you get the integral of secant, right? And the rule for how you do that is just a one-off trick that you have to memorize. You multiply by 1 in the form of sec plus tan over sec plus tan, and the derivative of sec is tangent squared, and the derivative of tangent is secant tangent, and so it becomes the log of sec plus tan. And it's a one-off thing, right? It's a one-time special rule that you have for a special situation, but this is a good one to keep in your mind. All right. So defining a, but again, the key here, exactly 2 threads, one enqueuer, one dequeuer. All right. So defining concurrent queue implementations, we need a way to specify a concurrent queue object. We need a way to prove that an algorithm implements the object specification. So in a concurrent setting, we need to specify both the safety and the liveness properties of an object. We need a way to define when an implementation is correct and the conditions under which it guarantees progress. So correctness is kind of most important. So we have sequential specification. So if some precondition, the object is in such and such a state before you call the method, then post-condition, the method will return a particular value or throw a particular exception, and post-condition continued, the object will be in some other state when the method returns, right? So you have something that looks vaguely like that. And so we have the precondition, the queue is non-empty. Post-condition, it returns the first item in the queue. And another post-condition is it removes the first item from the queue. And for the dequeue, we have the queue is the also, if the queue is empty, then we're going to throw, then our post condition is we're going to throw an exception, and the queue is state is unchanged. So interactions among methods can be captured by the side effects on the object state, and the state will be meaningful between method calls, and we can have our documentation can be linear in size with the number of methods. Each method describes what happens in isolation, and we can add new methods without changing the descriptions of old methods. That's kind of the ideal. But and that's what we like for sequential code. But can we do this for concurrent code? So we have methods, and can we document them in the same way? And is adding new methods going to be as easy? So the basic problem is methods take time. So we can invoke it, a queue.enqueue, and then the method call takes some amount of time, and then the response comes later. I mean, the return value is void for the enqueue, but it takes some amount of time to happen. In sequential methods, you don't care about how much, well, you care about the performance of your code, but generally you don't need to worry about how long your code takes because you don't worry about what's going on while it's running. But with a concurrent one, with a concurrent call, a method call is not an event, it's an interval, right? It's a range of time. And concurrent methods take overlapping times. So we can have 2 method calls and they can overlap, right? And with sequential code, we can describe everything in isolation. But with concurrent, like you take the filter lock or anything, we have to characterize all possible interactions with the concurrent calls. What happens if first this flag is raised and then the victim is set? You know, what happens if first one raises a flag, then the other, then the victim, and then, or what if flag raised, flag, victim, victim? You have to consider all those possibilities in order to make sure that your code works correctly. So think about this queue thing. What if 2 enqueues overlap? What if 2 dequeues overlap? And so on. So as I said, with sequential code, you can add new methods without affecting the other methods. You don't have to worry about overlaps and how they're going to interact with each other. But with concurrent code, potentially everything can interact with everything else in complex ways, which might cause you to panic. So the big question is, what does it mean for a concurrent object to be correct? What is a concurrent FIFO queue? FIFO means a strict temporal order. Concurrent means ambiguous temporal order. So here is our DQ method. We have our lock and unlock and all the logic in between, and that's going to be define the interval. So we could intuitively we could say the q.dq and q.nq methods overlap, something like this. And then you could further decompose those things into the time it takes to get the lock and time it takes to release the lock. And there's the NQ and there's the DQ. That's the actual code logic, inside the lock, excluding the lock and unlock methods. And those things are going to be, because of the way locks work, those things are going to be totally ordered. And the behavior will be sequential. All right. So here's a concept called linearizability. And what we're going to say is each method should take effect instantaneously at some point between the invocation and the response events. This isn't necessarily true for any method you write, but you should strive to write. One of the goals is to try and write methods so that you can analyze them this way. And the object is correct if this sequential behavior is correct. And then any such concurrent object is linearizable and we can reason about it nicely. So the example is with our queue in our that we're looking at. It's got all these different Qs and DQs on this. We're going to ask ourselves, is this execution linearizable? And what does that mean? So what that means is we're going to draw lines and we're going to pick a moment. Can we pick a moment in these intervals and draw the line such that the execution makes sense? So this says first we enqueue X, then we enqueue Y, then we DQ X, then we DQ Y. That makes sense. That is how the queue should behave. Therefore, this execution, this picture with these intervals for these particular NQ and DQ calls is linearizable. All right, so let's do another one. So is this one linearizable, do you think?
You could go Y, you could draw lines such that they don't overlap.
Well, so if I have an NQX and I have an NQY, right?
Mhm.
Which happens first?
NQX.
So how am I going to DQ a Y?
Oh, this is first and first.
Yeah. So no matter what I do, this is not going to work out. So this is not linear. If you observe this execution happening on your computer, it would not be linearizable. And normally you wouldn't observe this, but you might be debugging things and logging things and trying to understand how things work. And then you might realize something like this. How about this one? Is this okay?
I think so.
Yeah? Calvin, what do you think?
I don't think so, because I'm the operation that is complete.
It's not complete. It's a good observation that it's not complete, but the idea is however long this arrow is, I can draw a line in it. So I can put a line and say, if I can say this, if it happened here and this happened here, then it makes sense. And therefore it's linearizable. But sometimes you are going to have things that aren't complete like that. How about this one? What's that?
That seems to be okay, because
Yeah?
first thread queues X, the other thread queues Y around the same time, then you can DQ Y from the other thread because the other one is totally finished for sure.
Well, you can DQ the X first, right? You have to DQ the X first. If you NQ the X first, then you have to DQ the X first, but you can. You can draw a line here and you can draw a line there, right? So this is linearizable. But in fact, I could have made y go first, right? I could say NQ y first and NQ x second, and then I DQ y and DQ x. That's another way I could do it. Multiple orders can happen with this analysis and still be, if they happen that way, it's still okay. So this is a good sort of quiz slash homework well, probably just quizzes and tests. I can give you executions and I can say, is this linearizable? And then you have to decide. All right. So now we're going to have a different sort of problem. Instead of a queue, we just have a memory location, just an int, right? And we're going to read and write values into that int. And so whatever I wrote last into that int has to be there when I read it, or it doesn't make sense. So what do you think about this execution? Is this one linearizable? Probably not.
Your right one.
Yeah, my right one could happen. Well, it's not if it could happen. The question is, can I arrange them such that it does work? So I can say right one happens over here. I can say right one happens at the very edge of this arrow. Right? If I want to. Is there a way to make this work?
No, it would be 0 at the end because,
Yeah, I can't read 0 at the end.
yeah, it's writing, you write 2 or you have 1.
Yeah, there's too many problems for me to deal with there. So this is not going to be linearizable. And right here, read one means write one has already happened. So that kills that, right? And so I have to put it somewhere like there, and that means I'm not going to read 0. So it's not linearizable.
Do you write and then read before you can write something else?
Whatever you wrote last is the thing that you will read, right? That's the way integers work. And if I wrote a 0 here, and then I write a 1 later than this, then there's no way to read a 0, because there's no way that the last thing that was written was a 0. The last thing that was written, so the 1 is written after the 0, but before the read of 1.
So they're like.
Yeah, so that's right. It's just an integer. So I'm writing a 0 in, and then I'm writing a 1 in, and then I'm reading a 1, and then hell breaks loose, right? And I somehow write a 2 and read a 1. I don't know how that could happen, but that's what this computer did. It's misbehaving. And this write 1 happens before this write 2, so this is not linearizable. What about this one?
Possible. Because you can't read a 1 after you write a 2.
No, you can write a 2 before you write the 1, then you read the 1, then you read the 1.
Yep. Good. Tristan's right. You can write the 2, then write the 1. You can pick the lines this way because you get the freedom to pick. And your goal is to try and make it work, not to make it fail. And I can make this work. So this is linearizable. Okay. I think I would like to stop here. I don't want to barge too far ahead, but linearizable is a good thing. Hopefully it gives you it's a thing I want you to be. It's a very nice sort of bit of logic to understand, and it's good fodder for quizzes and tests. So I think that's a good place to stop. Anybody have any final questions? Yes.
Example.
Yeah, I can post the example logs. All right. All right. And Let me shut down then.